statistics. Sorry. Oh, what is this? I don't know. So maybe you have some more questions about my CV. Maybe about a couple of minutes for asking anybody who wants to know whatever about me. Anybody is okay, yeah, including the admin.
Yes, sir. If you provide information about your research, and that will be.
Ah, well, my first research was on basically economic theory. Although I studied statistics a great deal, but my PhD was in economic theory, so it was a some sort of a my research is more on theory than anything else in applied form. So I don't know if I'm very well qualified on statistics, but I always use statistics as a economic theory base for my research. So I've sort of my students have always used statistics, applied statistics as a tool, but I'm a theory person, I suppose. So I'm not very fond of working with data as much as the statisticians should be. But today I'm going to talk about how the data needs to be used for theory. That would be my, that's the only thing that I know. Apart from that, I studied physics as an undergraduate student. So I should have gone for things like the whatever the bosons or whatever, but I changed my subject to applied statistics and then to economics and then to back to mathematical economics. So that is the my research. My research papers are mostly on theory, but I've advised students on applied stuff. That would be probably the maximum I can say. More questions, please. One more, at least. I don't know. How can I see people's faces? I don't know. I don't seem to be.
Actually,
I
they
don't
have
know.
off their video, right? Okay. The participants off their basically video. Okay.
Oh, okay, okay.
Uh,
So, okay.
they are in mute mode. Otherwise, it is.
All right, all right.
Yeah. Sir, you
But
can start your.
they can
They
ask
can
me
talk off.
questions, I
Yes. Yes.
suppose.
Yeah. Yeah.
Yeah, can I start?
Yes, sir. Yes, sir.
Yeah. Okay. So basically, I'm as you see from my CV that I am a physics plus statistics plus mathematics plus economics person. So I might go back and forth in all these subjects. So the first point that if you have the thing on your, I gave a handout about the logical implications. That is the first and foremost thing that all of us should understand. Logic is very important. It's a sort of implication is the logical implication that we always study. So, as I gave an example, for a continuous and differentiable function, if you say something like local maxima, like at some point, then the first derivative has to be zero. That's the necessary condition, as they say. But if you go to a multivariate thing, multivariable thing, more than two or three, four, five variables, we go into the fifth or sixth dimension. So we have a maxima, we have something called a minima, and we have something called a saddle point. That is the important distinction that we make in mathematics about how the curves are formed, how the data is understood. We cannot visualize the data in about fourth or fifth dimension. We cannot even visualize even in two dimensions sometimes, but the point is of a maxima, minima versus saddle point. Saddle point is, as you know, that saddle is what you put on the horse's back, where you sit on it, and the horseback is sort of minima, and your legs are on the both sides, and that becomes a saddle point. But apart from that, there's the usual maxima, minima. Maxima is generally the mountain top, and minima is a valley. But it is important to understand what necessary and sufficient conditions mean. That is a logical part of it, as we studied in mathematics. But we have to look at the cause and effect. That's the next point. If somebody studies hard, then you can get good grades. That's probably some sort of a cause and effect phenomena. Although it's not necessarily certain that even if I study, if I'm genuinely stupid, then even if I study, I may not get a better grade. So it's not certain that cause and effect is a possibility, but not as much as a. I'm sorry. Oh, okay, okay, that's okay. Am I am I asked to? I thought I had given everybody a printout. Anyway, I don't know what everybody is saying, but that should be okay. We next come to the next point, which is randomness. Now, randomness is very, very tricky. Most of us are used to logic and emotions, etc. But randomness is quite difficult. And that's why statistics is different from mathematics. And I think it's one of the most counterintuitive subject that I have ever studied. And because with logic, you can say things like, oh, I know this, I know that, I know this, I don't know that, etc. But with statistics, you cannot be very sure, and that's what randomness is all about. I don't know if all of you are probably statisticians, know the subject very well, but to give you an example, there are a couple of things that everybody knows about, like says there are about 50 people in this room. There are about more than 50. But what is the probability that two people have the same birthday? Now, if you ask this to an average person, oh, that they would consider, oh, the probability is going to be very low because there are 365 days in the year and there are only 50 people here. But as we know that the probabilities are almost about 99% with 50 people, that two people have the same birthday. There's you can go and look up at the same birthday problem on internet, and it's quite nicely done. Another thing that happens with randomness is, suppose there are about, out of the 50 people, say 40 people are men and 10 are women. And let's say there are three sort of siblings for everyone, including the person. So that would mean about 150 people. And there are 50, I mean, there are a lot of people there. So, but there are more men there. And if you take the data out of the people, how many brothers and sisters they are, you will find that there are more men out of 150 than women, largely because the person who has arrived at this particular place is a man, and is much more likely to be a man out of male out of three. So effectively, you go back, and statistics tells you that you must do more about estimation than just averaging. So randomness is quite difficult in for a. That's why it is probably not taught in middle school or even high school. And generally, it's after you understand mathematics, then you go to statistics. Now, the next point is about variables. Variables. We know that there can be two types. It is discrete and continuous. Discrete means you just have this specific points on the real line, but continuous variable means that you basically do the entire real line, and you have sort of upper limits, lower limits, etc. But you essentially you have continuous. The variable can take continuous values, so it can be anywhere. So the essential difference between the two things is you use summation for discrete variables and integration for the continuous variables. And you do not use differentiation for discrete variables naturally. I mean, why would you use discrete? Because no, I mean, no continuity there. So we come to the first statistical thing that I would like everybody to know. I'm sure everybody knows it actually, but what is called coefficient of variation. Coefficient of variation is simply something that most of us learn in undergraduate classes, that coefficient of variation is basically what is called a it's an index, but it's an index of standard deviation divided by the average. Now these things are quite nice to use in the as a very simple statistical tool. Where standard deviation is what you that's a some sort of index for variation, and divided by the average. And the good thing about coefficient of variation is that it has no dimension. I don't know if you understand physics as much as many people do, but in physics, the units are very important. Like you have, say, acceleration is something divided by second square. So the units are important. And otherwise, I mean, if you have
Good evening,
the
sir.
numeric, sorry,
Sorry for the interruption. Sir, are you shared any PPT, sir? We are unable to find that.
Hello, already shared. It's an email as well as I WhatsApp.
Okay, if
Not
possible,
PPT,
please.
it is just doc file where all points are
Okay, sir.
there.
Okay, sir. Okay, sir. Okay, sir.
Yeah.
Right, sir. Right, sir.
I'm
Thank you.
sorry,
If
I should
possible.
have, I cannot upload here because I'm not
I have
very,
uploaded here also. In the
okay.
chat box, I already uploaded. Just I have
Okay,
uploaded.
thank you very much. Yeah. Anyway, so coming back to the coefficient of variation, the whole thing is about, it's a dimensionless number. The denominator and numerator have the same unit. So it's sort of index. Just to, I mean, we don't have too much time, but I'll give you an example of which is quite well known. Let's say take 5 temperatures in centigrade and Fahrenheit. So the centigrades, I recently got onto the aeroplane and it was quite cold outside, and, and as it turned out, it was minus 40 degrees in Celsius as well as Fahrenheit, and it was the identical. But as I studied in physics, that what is the only temperature that Celsius and Fahrenheit gives identical numbers is minus 40, but that's beside the point. If you look at the, say, 5 temperatures like 0 degrees, 10 degrees, 20 degrees, 30 degrees, and 40 degrees, and you convert them into Fahrenheit, they become 32, I think it's 53, 68, 86, and 104. And if you look at the coefficient of variation, the Celsius is 79% and the Fahrenheit is 42%. Now, I tried to calculate, I hope I'm not wrong. So the point is that when you talk about index numbers or whatever, the scale is quite important. And since Celsius and Fahrenheit use different sort of scales, the coefficient of variation is no good basically on that. So we need to be very careful. But having said that, we can use coefficient of variation, etc., for income distribution and stuff like that in economics, which is very, very nice, simple indices. So that is the background of what I'm going to talk about. Now, the first five points are basically the beginning, and I've already used 20 minutes, but maybe some people have some points to make on that. Let's have a minute so that we can go into the main subject. Anybody should be free to ask questions, please. I like questions basically, but that's not. I'll wait for about 20 seconds more if somebody wants to ask.
So can you explain the covariance example which you gave with the help of temperature once again, please?
The temperature is Celsius is basically a thing from 0 to 100 for the water boiling point. That's
Correct.
0 to 100. And Fahrenheit is from 32 to whatever the upper limit, I forget. But the point is that if you go from 0 to 10 to 20 to 30 to 40, the Celsius scale is 10, 20, 30, 40. These are 5 digits. But the Fahrenheit goes from 30 to 50, I forget, I've written some 50 or something, 68, 86, and 104. The point is that the variation for what we feel as a temperature is the same, basically. But as numbers, the variation is far too large for Fahrenheit. But average is also large for Fahrenheit. So as a result, coefficient of variation becomes rather small. So that is a point that I'm making, that when you use statistical data, you must understand that what is the scale of variation. Basically, if everything starts from 0, if Celsius or Fahrenheit started from 0, that should be all right. So as in physics, they call it Kelvin scale, which is a minus 440 or something. If you start from 0, that should be all right, actually. But the scale starting point being different means that you have to be very careful about variation and the mean. That is all the point. There's nothing great about it. So,
Thank you, sir.
okay, so we next come to the thing about what is called related variables. Now, related variables, I mean, it's quite normal for two variables to be related. Even you get any kind of data. Sometimes they call a sunspot theory. If there are lots of sunspots on the sun, then the Indian economy goes up, let's say. It's a sunspot theory. Basically, it's just totally random. I mean, there's nothing. The sunspots, I'm sure, do not affect the Bombay market as much as they affect the entire world. But it is possible to construct a relationship. That related variable, I mean, you can always relate two variables together, but that's not so important. What is more important is the next point. It is called covariance, which all of us, you know what is covariance. Covariance is how do we do sort of react with two variables and how do they vary together. Now, and if you look at the paper, that's the formula for covariance. Covariance is simply the expectation between the two variables and the differences between their means. And covariance is very, very good in terms of as a concept to understand because it is useful for people like economists, etc. There's an example there which is, I mean, I just gave it for the reason, for no extra reason. But if there is the demand of apples is 16, 12, and 8 kilos for the price of 4, 5, and 6 respectively. If you look at it, the covariance can be calculated, and it is generally, their basic covariance means they're negatively related here. The prices, when price goes up, the demand goes down. That's a standard thing that we study in economics. But when we have this thing about demand and prices, we have a causality in some sense in our private lives. If we don't go and buy costly things just because a lot of people have a lot of money, so they don't care for the prices. That is possible. But effectively, for average person, we sort of go and if it's costly, we do not buy that stuff. And that comes to our first topic, which is correlation. The correlation, everybody knows what is correlation. I'm sure I'm not. I should not be wasting too much time on it, but I think we should understand that it was given by a lot of people who did it before him. But Carl Pearson was a great English statistician, and he decided that there must be a correlation between two variables and how to estimate that. Basically, it boils down to what is called covariance and how much covariance is what two variables move together, but variance is what one variable each moves in its own on its own. And so he came up with this beautiful definition of correlation coefficient, which is called rho, 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 as the Greek letter says. I've written it in Greek, but I could not, my poor word does not allow too much of a beautiful Greek language, but that's okay. Anyway, so the point is that rho becomes a symbol for what is called correlation coefficient, and that we all know that it's a beautiful concept, and it does not go below -1, it does not go above +1, because we know by something called Cauchy-Schwarz inequality that the the correlation coefficient is not going to be below -1 and above -1, so above +1. So it's quite nice to have a correlation coefficient, but the essential part is that he never asked for a causality in the thing. It was always completely random. I mean, you could look at two variables and the data, and there's no causality involved. But I personally like the next point, which is rank correlation, which is another Englishman called Spearman. These are all early 19th century, late 18th century kind of people. I mean, they dealt with biostatistics. They worked with various data that was available, and Spearman was more interested in not as much as the connection between the relation between the two, but actually the grading of it, like 1, 2, 3, 4, 5, 6. I mean, rank, that is what it is. So there's an example about people students who study and who do not study, etc. Please look at the thing. The point is that the index is very beautifully defined in terms of ranks, not as much as the actually value of the variable. And the statistic is, as it appears on the paper, 1 minus something something, etc., etc. That's a Spearman rank correlation. Why I think is more important than the earlier correlation coefficient is that, for example, I don't know if you know something about HDI, Human Development Index, as they call it. This is a very popular thing for the journalists, for economists, etc. It depends on three things basically. Something called longevity, in how long people live in their life. The third is education. The second is education, and the third is the per capita GDP of the country. So it's called. It stands on the three legs as L, E, and G. That's why I call it three legs. Basically, it's a joke. Basically, the point is that actually, I asked one of my students to work on it, and it turned out that the rank correlation between all the countries that are ranked with L, with E, and G, the rank correlation is about more than 95%. So what is the point in getting three different variables and then averaging it out and making an index if the three variables are so closely linked with each other? So rank correlation tells us about how good the variables are linked. And I actually found out that it's much better to come up with an index with, I mean, there are countries like Cuba or Azerbaijan, ex-Soviet things. What happened with them is that the Soviets pumped in the money into the countries, so they live long, their education is good, but the GDP is low. But if you look at the Human Development Index, they go down by itself. But the life there is quite nice. I mean, a lot of students Indian students go to the Central Russian ex-Soviet republics to study because life is good there and it's cheap and the quality is good. Now, a lot of people are stuck in Ukraine. That's a different story. But the point is that Human Development Index is a flawed index because rank correlation tells us that you can either use one of them, a longevity or uh, education or GDP. Either would work out quite fine with as an index. There's no reason to combine the three. And in fact, I came up with my student with an index so that the countries who effectively work more than what is expected, they should be given more weightage in that index. And we came up with really remarkable re-indexing of the thing. Anyway, but my student actually was lazy, so he just left and got married and never published anything. So that is besides the point. But I think the point is of rank correlation is that it gives you a nicer view of what statistics is all about. And I think at this point, I think again, I might have some questions because we can go down further, but the correlation part is important here. Correlation of two coefficients, Pearson and Spearman. Probably people should have questions. Please do so. Can I have at least one or two? Please feel free. Anybody, please. I'm not very I'm quite useless in talking one way. I prefer people to ask me questions. So please, at least one. No interest?
So when do we use, actually, can you give us insight about when can we, I mean, when is the right situation to use Spearman in this one, sir?
Yeah, it's basically the difference between the two correlation coefficients is something called linearity. The Pearson coefficient is essentially for linear understanding, and rank is essentially for what is called monotonic thing. So monotonic is something like it could be curve like this going up and or this way, etc. So the rank correlation essentially is monotonic, and Pearson is essentially linear, which is line. That is not, I mean, line is also monotonic, but monotonic is not always line. That is the difference, I think. What is the best I can say. So if you go to Wikipedia and look at the rank correlation, you will find a beautiful curve there where the entire, I mean, it goes up like this and then goes beautifully up. And two variables are completely lined with, I mean, they're monotonic, but they're sort of S-shaped. S slightly, not S exactly, but slightly S lying on the bed, basically. But if you look at only the linear part of it, then you will not get a solution. It's important that the monotonicity of a data is quite important for Spearman rank correlation. And if you insist on using Pearson correlation on something which is monotonically nonlinear, you will get a bad result. And basically, I think it depends, as I would always say, that most important part is that what are you trying to get at? If your research
अरे भाई साहब मेरी हालत खराब हो गई कहाँ
sorry,
रह गया हैं अभी तो सर एक मिनट
Please
तो
mute your mic.
I'm
Arvind
sorry.
Ramesh Gupta, please mute your mic. Avinash Gupta.
I'm sorry. Did I do something wrong? No, probably not. There's somebody talking. But anyway, not so important. Anyway, I'm coming back to my topic, which is basically that Spearman versus Pearson, and it's basically
Sir,
linear versus.
I have a question. May I ask?
Yes, please, please, please.
Sir, can you explain a little bit more about Pearson correlation coefficient R? Can you give us some brief for this?
Pearson,
Yes, sir.
I should Pearson coefficient is, as I said, that is written there. I thought I wrote it. It says it's given by the ratio of the covariance divided by the two standard deviation. It's just an index number. So basically, covariance and the standard deviations have the units. They're squared units from the denominator and no, up and below. So it comes to the covariance divided by the standard deviations, the product of the standard deviation. But it was a very, very logical thing for people to do in early sort of statistical analysis about various things like biostatistics or psychometry or whatever, because essentially what it means is that you are doing what you're looking at two variables covariance and divided by the standard deviations. So it gives you some sort of understanding about how much they vary together and divided by how much they vary by themselves. So that's an index, and it goes from -1 to +1. So if you have Pearson correlation coefficient is 1, that means it's the two variables are so closely linked that there's no sort of problem over. You can always say that they're the same basically. Or if it is -1 also, they're completely opposite of each other. If it's 0, then it means usually they're not related or they're independent. And that's roughly what is said. But it's not necessary that, as I wrote there in the pages, that variables can be completely related, but the correlation coefficient could be 0. But that's if you have a non-linear thing, like y is equal to x square would have correlation coefficient at 0, but there, I mean, as you can say, y is equal to x square is completely linked with each other, but that's a non-linear thing. So that is the point with Pearson, that it's essentially it talks about linearity, not as much as non-linearity. And rank correlation does not worry too much about the linearity versus. But anyway, I don't have too much time. Let's go to the next. Something called testing for significance. We all know that testing for significance of any coefficient is important, and there's the point number 10 is it's just I mean, for those who are interested in further study should look at it, because what is called Fisher transformation and what's called t-statistic is what we study in math stats, but I mean these two coefficients are distributed completely differently, and so we should be careful. Anyway, let's go to the next thing called dependence. There's something called why do we have covariance, correlationship, etc.? Because we in statistics we do not really think about dependence. We think about randomness, and both the coefficients are not necessarily for understanding what is a dependent variable or what is an independent variable. As a bit of a joke that I there in the thing that when women have to when they have long hair, then the demand for ribbons and combs goes up. But if you want women to have long hair, you cannot just raise the demand. You cannot raise the production of ribbons and because something is dependent and something independent. Basically, this also works with a lot of economics. I don't know if you are interested in economics, but it is possible that when we produce more, then if people demand more, they spend a lot of money, then the demand for money goes up. But just because the production goes up and the demand goes up, it's okay. But you cannot do it other way. Like what Americans are doing now, they're printing dollars left, right, and center. And they're not producing much in the country. And as a result, I don't know if you've been to America recently, but there's a phenomenally high inflation. That's because if you pump in the money, they're not going to produce something. This just goes to increase the prices. So what is the cause and what is the effect? What is dependent or independent variable is quite important for further analysis. So I think dependence is quite important. There's a difference between what is called dependence in vectors and dependence in statistics. So let's not, please, I'm sure all of you are familiar with the mathematical definition of dependence, but this is dependence in the statistical sense. And that's what comes to our next topic, which is called regression. Regression is basically correlation with dependence and independence. So correlation essentially meant that you don't care about which is cause and effect or whatever. Both the things are random. But with correlation, as compared to correlation, regression means essentially that you want to know how the two variables are related. And that's what gives you the idea of regression. Now, regression essentially, I don't know, please look at the number 11 point of the thing. So it's usually normal for statisticians to have y as a dependent variable and x as an independent variable. That's the nomenclature, basically. Not now we can do it other way, but y and x are. So y is equal to fx is what is called a regression. Regression meaning you want to analyze what is the kind of correlation that these two variables have. And y is equal to fx is basically what the function fx, as in mathematics, is called. So I don't know if you're familiar with the history of sciences, etc., but the orbits of the, say, what is called Dhumketu, what is called the comets in, or for that matter, small asteroids, etc. They are calculated according to what is the best that they get, the fastest they can go, and the mathematics behind it is always they look at they minimize the kind of effort that they make. So it's a cost basically, that why would a comet would come this way all the way to Earth and go back? Because that's the best possible way for it to come and go back. And that kind of mathematics was devised by, I mean, from even before Newton, etc. But two great people called Legendre and Gauss, they actually developed a very nice thing about what is called a principle of minimum squares. So the minimum square is essentially what you want to minimize the error that you can cause, and you want to maximize whatever the best way you can achieve your whatever you want to do. And that is the essentially the important part of the regression analysis. And that is very important because we do not realize that regression comes from celestial bodies and comets and various satellites, etc. We send satellites in orbits now. What is the best way to go to moon, for example? That would be calculated by the least squares, and I'm sure the ISRO scientists know the subject very well. That's why we went to moon at the cheapest way, etc. But that's not important. We are talking about regression. Regression actually uses that concept of minimizing the error. Now, if you, I do not have too much time left, but let's look at the number 12. Okay, that's probably the easiest to. Why linear regression is important is that if you have nonlinear connections, you can actually transfer the variables by trigonometric things or logarithms so that it sort of becomes a straight line in the new data. For example, a cost curve would be an inverted S curve in economics, but you can always take a point of when the slope changes as the break point, and then you can use the bottom side and up side as and convert it into logs and get into a straight line. So basically, why is linear regression is so important is because even if you have if you have non-linear connections between two variables, you can always take logs and trigonometrical function sine or cosine or whatever, and or tangent for that matter, and then get it converted into a new variable so that the two variables are linked in a straight line. And the most important part is that I don't know, you look at the number 12 point, that there's y minus a minus bx. This term is essentially an error term. Because y is a dependent variable, x is a independent variable, and y minus a minus bx would be a link between the two. That is the linear regression. And what happens is that you minimize this thing looking at the data. Now, when I studied mathematics as a student, I understood what is a variable. But at this point, there's a very clearly x and y are variables, yes, but when you have a data, they become observations. So that you have a data and you want to fit what is the regression, and a and b are the parameters. So what are the best a and b parameters that you can choose? That is the point of linear regression. And as it's written there, that you can always minimize the error terms and you can arrive at the estimators, as they call, not estimates, but estimators. And A and B are estimated according to what is written there in number 12. Please look at it. Please look at any textbook or Wikipedia for that matter. The point is that the coefficient, not the coefficient, but the parameter B turns out to be related to the correlation coefficient. So B is equal actually Spearman's. No, sorry. Yeah, B is Spearman's coefficient into the standard deviation sigma x divided by sigma y. So that is, in some sense, why linear regression is completely related to Spearman's correlation coefficient is because of the linearity. And with due respect to all the people who like non-linearity, etc., for a person, average person, linearity is the most important part. If you find that there's a link between two variables with linear connection, people are quite happy to know what is happening. So basically it means what we always know. If something goes up, something else goes up, so it's a connected linear. It could be non-linear in many ways, but what we want to know that how good are the linear connections possible. And that is why the regression analysis is completely dominated by the linear part. And that comes back to covariance and the standard deviations. And that is why the linearity plays so important role for the Spearman correlation coefficient and regression analysis. But having said that, I'm not saying that they're not good. For example, I was taught by somebody called Professor C.R. Rao, who is a great statistician. Many of you may have heard of him. He developed something called MINQUE, minimum normed quadratic unbiased estimators. Now, it was early 70s. His three papers had come out in big journals, and he was teaching us. So he said, this is the best thing that has happened. And we were made to study. But believe me that after those three papers, nothing ever came up as a path-breaking thing after that. It's called, please look at MINQUE, MINC as it's called. And just because for my sake, my professor C.R. Rao devised that. And I was made to study and I got my credits for that. It gave me a good grade actually. So the point is that linearity versus non-linearity is the most important part in regression analysis. And if you go in a non-linear thing, nothing great is achievable. So it's possible for me to say that, correlation coefficients and regression analysis is essentially a linear thing. For example, if you look at the cost functions that are defined in economics, they're inverted S curves. Like, I don't know if you can say this. It like goes this like and then goes up basically. So it's you have to use the third degree equation ax plus bx square plus dx cube. So it's just not a third degree murder or anything, no, just a third x cube you have to use so that you can do the justice to the cost curve. But it is quite difficult to sort of do econometric analysis or statistical analysis on that curve. It is so much nicer that you do a linearity, take logs or whatever you want, and do linear, so that the effectively what we have the tools available for linearity. We do not have good tools available for non-linearity. And I'm sorry, I'm just going to come to the end of my, I don't know, how much time do I have? I still have time. Okay.
Sir, up to 7:30. Up to
Huh?
up to 7:30. We have more 30 minutes.
Okay, good. So I have no trouble with timing. I'm just about 3.5 hours ahead, so I was not sure what. Okay, good. So I think let's go back to a little on the linear regression. The linear regression part was, please look at the number 12, okay? Linear regression being the y minus a minus bx, and the data is differentiated. I mean, that data is differentiated with respect to a and b. Now, the problem with mathematics versus statistics is that mathematics uses variable as a concept, where you differentiate with respect to variables. But this method of least squares or whatever is essentially wants to arrive at a parameters a and b, and the parameters are, in this case, parameters become variables in the sense of differentiation. So when I went to the Statistical Institute, actually there were 11 of us, and I had statistics background, but about 5 of them were maths background, and these guys got thoroughly confused between this. What is this differentiation between by parameters? If you call something variable, you have a variable, and you differentiate with the variable. You never differentiate with parameters according to mathematics. But the point of statistics versus mathematics is that you have to understand that you have a data, and that becomes your observation. I mean, that is what you have. And then you want to maximize or minimize whatever you want. Like in statistics, you have maximum likelihood estimators or minimum variance estimators, etc. So I think the most important point of difference between statistics and mathematics is that maths does not sort of, is not an applied subject. It's just an original subject. Statistics is completely an applied subject. That's why it is not taught in elementary schools or even high schools mostly. You learn it after you study mathematics and logic. And it's quite counterintuitive in many sense. So one of the important points I want to make about linear regression is that the parameters are important, and here the parameters are a and b. But if you go to non-linear equation, like earlier I talked about the cost curve, like ax plus bx squared plus dx cubed. Now, if you want to estimate them according to the minimum sums of squares, that it's quite easy to do that, but it is important that when we have linear regression, we have this great thing about the assumption of the error being distributed with mean zero and a constant variance. Now, that does not work with nonlinear regression. And I think most of the statisticians stick to linearity because of the beautiful nature of the standard term being distributed like a normal distribution and with a mean zero and standard no, and variance, constant variance. But the thing is about the linearity versus non-linearity, and I think that is quite tricky in terms of regression analysis. But I think before I go to the advanced topics, like, I don't know, I can mention it, but maybe I should have questions before, but something like, I don't know, something, 2 points of interest for statisticians are autocorrelation and something called heteroscedasticity. I don't know. Autocorrelation is something that a variable is over time series, and it is autocorrelated in the sense that it is related to itself. Auto means itself, and autocorrelation is something that the variable is linked with itself in the past. That's a time series thing, if you look at it as a time series. So if you have a data and if you think that the things are related with itself in the back, so that's a great amount of information that is available to you. Why should you not use it? That is the point of autocorrelation, basically. So there's a autocorrelation. You calculate the autocorrelation and use it for estimation in terms of, so you can predict even better than, for example, I don't know if you know, there's something called Brownian motion. Maybe some of you know, maybe some of you have not heard it. Brownian motion is something that is linked, a variable is linked with a 1 year past. That, like, my income is about 5% more than my last year's income. But autocorrelation can go back further. But Brownian motion essentially means that it's only linked with 1 year before. And it's got no connection with what happened 2 years ago. So that, I think, if you look at correlations and regression analysis in that context, you can have better insights if you know how much of correlation is between the two consecutive years. It's also called drunkard's man's walk, if you remember physics, etc. How far the drunkard man can go from a lamp post. He's just holding onto the lamp post and he just goes somewhere and comes back. So that is a drunkard man's walk. But that's what is called a Brownian motion. But these are time series analysis, and I'm sure many of you have heard of something called Box and Cox. Box and Cox, they are two famous scientists. Actually, originally is Box and Jenkins, but the book became Box and Cox basically because of the Americans loved the book anyway. So you have this time series analysis, which is linked with autocorrelation, and you use that to get a beta estimate. That's the part of the correlation regression analysis, which is quite important for people who work with data on, say, stocks or shares, or how the rupee is not a good example, because the rupee is quite closely linked with dollar. But if you look at where I live, Japan, the yen and dollars are not linked with each other directly. So they very great deal. I mean, at some point of time, long time back, when $1 was 80 yen, I converted everything, all my money into dollars, and then I made a huge amount of money, because then the dollar went to 130. Now I'm in trouble because now the dollar is 150 yen. So, but it doesn't matter to me at all. But point is of how do you, I mean, it allows you to, time series allows you to do the regression analysis in terms of over time. And I don't know if you are familiar with this REM models, autoregressive moving average model. The point of moving average is, I mean, if you look at the statistical data and you look at the differences between consecutive values, then it gives you a trend. Trend is what you look at for how the stocks go up, how the stock market is going up, etc. But then you have the second order derivative, not derivative, but the difference. And then that gives you seasonal fluctuations. So these are the sort of applications of correlation and regression. And but they're nice because it's easier to understand how linearly they're moving in the time zone. Another main point would be what is called heteroscedasticity. Heteroscedasticity is, this is a very big word, nothing great basically. That it just means that sometimes the variables have an error which is not, it does not have a constant variance. It varies depending on its level of calculation. So sometimes bigger, the higher the level of variable, the bigger would be variance of the error. So the variance of the error term can be different, and that's a good information to have, so that you can use that information to bring it back and get a better estimate of what you have. So these two concepts are quite important for, but as I said, that they are linked with auto correlation. Basically, it says linked with the time series, and heteroscedasticity means not a uniform variance. That is effectively the term. So it is. These are the additional things that you have to look into if you want to have a better estimate than what you actually can achieve by just simple looking at the data. Having said that, you must not get into this fallacy of first calculating ordinary least squares, etc., and then go back and use additional things to get better estimates. No, the first important part is that you first test for autocorrelation coefficient, heteroscedasticity. There are tests available for that, for the data. And if the tests say that there's a positive reason for you to include them, then include them first. Do not include them later on, because the testing goes down if you use something that's cheating. Basically, you first do the data thing and then, oh no, it doesn't work out, so you add on some additional thing. No, you should not do that. It's very important that you understand what you're doing and first test for various things like, um, suppose, I don't know if you know, there's an animal called platypus. Platypus is an animal which is not normal distributed. Normal distribution sort of goes to zero on the thing. But platypus is sort of thick at the end, and his a spout in the mouth and a long tail. So it's a thick. So distribution can be platokaryotic, as they're called, and you have to be careful about how you should approach statistics in terms of the error terms. Because if the error term is platokaryotic, and you should not be using standard thing, you have to use specific models which cater to that kind of phenomena. And so in many ways, regression and correlation are simple, they're nice, they're good for students to understand what to arrive at, but there are a lot of pitfalls in terms of how do you go about doing the regression analysis. For example, I don't know, there's a nice thing about welfare economics. Like, I have no idea if you understand, if you know about how people are happy in various countries. There's a very nice study for Americans versus Japanese. What happens in Japan is that young students have a great time, young boys and girls. They have a great time till they are in the elementary school, and then that's where they start slogging it out. And they are miserable for middle school and high school, where they really slog it out. They have to study a lot to get into university. But once they get into university, they're so happy. They don't have to study much. They just have to graduate, they get a job, etc. And that's when they they get employed, and then they have to slog it out. They have to work hard, and they become miserable. And then they grow up, they get married, they become more miserable according to the study. Not so important. I'm sort of a joke, but then they keep on going, they do not get divorced, they keep on going, they have their kids there to bring them up, and they keep on having the life become miserable all there. So the peak is when they just are in the fourth year of the university. That's the highest level of happiness for them, according to the data that the professor got. But if you look at the American counterparts, the Americans basically there are a lot of rich Americans whose parents or grandparents pay for their education, but most of the American students sort of leave home around 16 and their parents throw them out or whatever. So they're miserable till about 2022. And then they sort of go back to the university, then they go back to job, then they get married, they're happy. Then it's a bit of a joke also. then they get divorced, they're more happy, and then they get married again, they're even more happy, and etc. So the point is when you look at the data over time and data over cross section, you have to be very careful about using regression and correlation, because time is not necessarily a good sort of dependent variable. It really is not a. I mean, there could be reasons why you want to use time as a dependent variable, but you have to go to some kind of theory to use a dependent variable versus independent variable. And I think the point about correlation and regression analysis is how beautifully can you choose the variable and how can you analyze it completely? How do you analyze it well? I can go on, but I think I should have more questions, I think. So must be time for questions. Please, anybody.
Hello, sir.
Yes, sir.
Uh-huh. Sir, in statistics, when we are calculating the coefficient of correlation coefficient and coefficient of, so R square and R, the calculated value of R, if we square down the calculated value R, it will give the R square. But what is the physical significant difference between these two?
Now, R is a correlation coefficient. R square is a statistic by which you estimate about you. If R square is good, then the fit is good. That is what roughly means. Okay? R square is a R, capital R, okay? R square. Capital R square is essentially how good is the estimate that you have estimated. And R is a correlation coefficient, R, small r or rho, whatever. So please understand that R square is a statistic, as it is called, and it is, the higher it is better it is, okay? That's the best, I can say. The Spearman's correlation coefficient is between -1 and +1. R square can be more. I mean, there's no. It's a different distribution. I'll need to have another session if I have to go into R square. But point is of what are called statistics. Okay, statistic in the sense of not in the subject, but T is a statistic. R square is also a statistic. And they're distributed in many ways. So R square is, if your R square is good, then you have a good fit, basically. That I think you should understand. But the R square is not completely linked with, I mean, it is linked somewhat with the Spearman's R, but R square is a statistic. So please be careful about when the computer, that's a problem these days with softwares. You just put in the data and they give you the R square value. But you must understand what is R square and what is the distribution behind it. I think, I think I cannot, I'll need for 15, 20 minutes more if I want to go there. So please understand that R square and R are different things. More question, please.
Thank you, sir.
Please, waiting. It's getting to be 11 o'clock here in Japan, but that's okay. I'm still awake. Please.
Sir, you have any YouTube channel of yours? Because the session is so insightful that we would like to watch in the future as well.
Oh my God, you are asking for trouble. I'm a very bad sort of YouTube person. people come to me and people sort of write to me directly. I think if you best thing is to write to me directly
Yeah,
and ask me
yeah, we will
questions.
do
I
that,
think
sir.
I don't do not I do not I'm not a media person as much as I'm just a ordinary professor. So
Okay.
I'm sorry.
Okay.
Yes, sir. Yes, madam.
Sita, I can.
Sorry.
Yes, Dr. Sapna. Yes, participants, if you have any question, you can ask.
Please. You can
Sir,
ask me about anything about Japan or anything about me also. That's not a problem. Please go ahead
Sir,
and
can you explain different methods in statistics that we use estimation methods? There are different
okay.
methods. Yes.
Yes. But I think basically what has happened recently in statistics is that we sort of depend on the statistical softwares. Now, the problem is not as much as software, but why do you want to use one particular thing? I must say that my statistics is a little bit dated because when I studied, there's no great computer available, etc. So we used to study statistics on first principles. But now statistics has changed quite a bit in terms of models of computers. So it me as a person, but I think recently statistics has gone down in terms of theory in the sense that people are so much dependent on the apps that they do not even bother about what they're doing. Like for example, bootstraps model. It is a bootstrap model is a very nice model these days. Apparently in econometrics and statistics, it's a non-parametric thing. That is also okay. No great problem, but it is difficult to understand what is happening there. So I personally think that whatever problem you have in mind, first look at the problem and then decide on the software that you want to use. I would not recommend any sort of estimation method just because it's there. So whatever it really depends on what problem you're working on. And
Sir,
I'm sure you
how we can
sorry.
identify that particular issue? Which estimation method that we can apply? How we can identify this?
That it really depends. Personally, I think it depends on what subject you are working at. For example, if you are working on something like environmental studies, if you are doing environmental economics and you will be working on some problems, like in California, there are fires available going around all the time these days. Now, if you do not have that fire as a variable in the model, it's no point in doing like my son works on wine industry in Oregon. He's got his PhD, etc. But I don't know why he works on wine, but that's okay. It's his problem. So, but if he wants to work on wine industry, then he has to look at the climatic changes, how the climate affects the quality of the grapes or whatever, because Oregon could be very cold and there will be wines which are good. The grapes would be good for some grapes would be good for some wines, but some may not be. And I think his job would be that he has to look at the variables and use the statistics depending statistics applications so that he understands what he is driving at. So I think statistics is not a subject on itself anymore. I think it's an applied subject, and you must realize what is your basic topic. And after that, it's easier to use the applications or whatever high quality stats applications are available. But please do not use the application just for the sake of there, just because they are there. So I think should, but I'm not qualified. Yes, sir.
Sir,
I
good
have a
evening, sir.
question.
Sir, may I have a question? Ravindra, sir. Very good evening. Sir, I'm Dr. Ravikant Makarla from Malared University,
Okay.
Hyderabad.
Hi.
May I have some common data sets, sir, regarding your economic so-called. I served in Africa earlier, therefore, just it's finding a bit difficult in India to find like G20 countries or certain groups when we take into consideration how they perform as a group, and what are the dynamics of having some countries into a group. Are they really benefited out of it or not? Something like Russia, India, and we have SARC and other things, right? There are many agreements are there. Therefore, these groups have the dynamics of this grouping of countries. And can we get any data specific to these groups?
You know something? I'm a statistician, but I hated data. That's why I moved to economics basically and mathematics. But largely because our data is so very difficult to get. Good data, that is, I mean, original data, etc. Because most of the data guys who collect the data, like my friend called Pranay Roy, I don't know if you remember, if you know him, but he was a data analyst on elections, and he basically said that when Indira Gandhi was elected with a huge majority, he was working for India Today those days, and he got data which was simply unbelievable. So he decided that all these data people have gone to the chaiwala and picked up data and came to him. But that does not work. And I think the quality of data is extremely important. And these days, I think, that's my personal opinion, that statistical agencies do not have free sort of freedom to collect data on a sort of free basis. A lot of governments interfere. They sort of say that no, this is not done, etc., etc. So you are asking the wrong person about the data quality. I think I've stopped using data long back. My students use it sometimes. They get it, and then I ask them, is the data good enough or etc. But I'm not. Oh, the next session is on.